Can you believe in the mess we are right now? What kind of trouble? We have, described the skeletal muscle as an organ, first as a tissue, then as an organ, then we describe the cellular component. That now we're diving into a little bit of the molecular part just to understand the basics of muscle contraction. So this is a very cool uh, illustration that shows you in red the myosin um, fibers, the myosin filaments, and in blue the actin filaments. They're kind of twisted in there. So what happens is that the myosin filament consists, as I showed you in a slide in the previous, like in here in the previous video, it consists of all of those little heads or myosin heads, and these myosin heads have this neck, and the neck can pivot like this, like that. Remember the cilia? So they can push in one direction. So what happens is that when the calcium is released from the terminal cisternae part of the sarcoplasmic reticulum, which is the endoplasmic reticulum, smooth one. So when the calcium is released from there, it interacts with the actin, and some changes happen in there that uncovers or make available the site on the actin to interact with the myosin head. And then the myosin head grabs the or attaches to the actin filament right on this place and pivots, moving the actin filament towards the midline. So, and this is happening at the same time on the other side. So both myosin heads move um, the actin filament towards the middle. So they attach, looking in our, where's my cursor here? This is the head, the myosin head attaches first to the actin. It pivots, moving the actin filaments towards the M line. Then this consumes ATP provided by the mitochondria. So the ATP is broken down, energy is released, blah, blah, blah. The thing is that uh, then this myosin head detaches, pivots again, it goes back to the resting position to grab again the same actin molecule um, or filament, but further distally from it grabbed it before. So it, it pushes in here, grabs the actin filament in here, it moves it to the middle, and then it detaches and grabs it distally so it can move it further or closer to the M line. Let's see, this illustration didn't help, maybe this one does. So if you have clear, because otherwise this won't work, but if you have clear the anatomy of the sarcomere, you can understand that here in the midline we have the M line. And in here, these are the myosin filaments with the myosin heads. See how the actin that is attached to the Z line on either side moves towards the middle. Look at the direction of the of the arrows. So the myosin head attaches and bringing closer to the M line, the myosin head, the actin filament detaches and grabs further closer to the Z lines. See, it grabbed first here, now it detaches to grab the actin filament closer to the Z line to move even more the actin filament towards the midline. This is how we shorten. See, this is the relaxed sarcomere, and compare the width of this sarcomere with the width of this one, which is contracted. So we are shortening the entire sarcomere. Now, there's several things that we need to be clear in here. The sarcomere shortens, of course, during muscle contraction. That's what shortens the entire muscle. But the myosin filament and the actin filament do not change their length. How come? Because this is called the sliding filament mechanism. What is, as today, what we think it happens is that since the myosin and thin filaments, they overlap, okay? What they do is that they slide past the other, and and that's how they shorten. But they do not, the length of each of these fibers do not get modified. It doesn't change. So the length of the entire myosin filament remains the same. This is the relaxed, and look at the contracted. It's the same length. Look at the length of the actin filament. It's the same. The thing is that in here they are away from the M line, and in here they have been pushed together to the M line. So this is a fully contracted sarcomere. So what happened in here is that the two Z discs got closer together, shortening the entire sarcomere. See that this contracted sarcomere is shorter than this one. So Z discs are closer together. The length of the myosin and actin filaments remains the same. Look that the H zone, what we described as the H zone, this area disappears, okay? And the length, or maybe the width of the I band in here, containing only the thin filaments, decreases. See, now it's thinner. Well, it's this one, okay? So in here, this is how it looks in reality. This is the pattern, the striated pattern of all of the sarcomeres on the skeletal muscle fiber. So in here, they are in relaxed. This is the Z line, Z lines, and see, this is the A band. There is darker than the I band. There is lighter with a Z line in the middle. So see that the A band from here, from here to here, that's the A band. Compare that to this A band. It got shorter. Now compare the A band. Let's see the A band. From here, containing only, thick and thick filaments, it remains the same, pretty much the same. It's this one. So the width of the A band remains the same because the myosin fibers do not shorten. Now, the I band, it changes length, but not because the actin filament shorten, but because they slide towards the M line on top, or slide on top of the myosin filaments. This mechanism, the sliding filament mechanism, explains concentric contraction. Concentric contraction is the ones that we're used to when the muscle shortens when contracting. But there is another type of contraction which is eccentric, out of ordinary. The eccentric contraction, the muscle doesn't shorten to when contracting, but it lengthens. So this contraction happens when we are opposing gravity, when we are performing a movement opposing the force of gravity. So lifting or flexing the forearm at the elbow, this is concentric contraction of the biceps brachii. But to reverse this movement, I have now to contract eccentrically the triceps brachii to move down towards the center, the or yeah, to resist gravity, um, in a way that the motion or the movement can be smooth and gradual. What else? So again, in here we have the contracted sarcomere. This shortens the sarcomere since all the sarcomeres are repeats in the entire skeletal muscle fiber. It shortens the entire skeletal muscle fiber. Since the skeletal muscle fiber is surrounded by endomysium, and the endomysium is continuous to the perimysium and epimysium, this uh, shortening is transmitted from the muscle fiber to the muscle fascicle to the entire muscle, and the muscle contracts. Voila!